So this is our graphing with the transformation rules notes, the back side of the notes. And what we're looking at is we're looking at graphing functions without a calculator using our transformation rules. And we need to be able to identify the parent function to start. And once we identify the parent function, then we're going to apply our transformations to them. So as we look a little bit more closely at example number 4 here, our parent function is the function with the double brackets there. And I oftentimes call it the greatest integer function. Also in our notes we called it the floor function. It looks like a bunch of stair steps. Hard for me to draw on such a small graph. I'll do the best that I can here. But there's going to be a stair step there. And again, I'm really sorry. It's really hard for me to stay on those steps. But hopefully you get the general idea, and hopefully at least you can make a better picture on your paper than I can make it on mine. But one there on this side, on the right side, they're all open circles. So when we get into our transformations here, this one only has 2. The first one is coming from this 3 that is out in front of the function. What does something out in front of the function do to the function? It's going to be a vertical change. In fact, it's going to be a vertical stretch. And since it's 3 there, it's going to be by 3. So what's going to happen here is that where our stair steps are going to change. Now, not the 0, not the first step. It's going to remain where it is. And that's supposed to be an open circle there. But now, the vertical distance. If you look back at the parent function, the distance between each step is 1 space. Now the distance between each step needs to be 3 spaces. We have a step at 1. 1 times 3 is 3. So we're going to have a stair step here. And then our stair step that's at 2 from our parent function, 3 times 2 is 6. There's going to be a distance again of 3 in between there. And again, that's supposed to be an open circle on the right side. We can do this or follow the same pattern when we go down here for in our negative stair steps. We had a step at -1. Now it's going to be at -3. And again, very hard for me to draw. And then at -6, we had a stair step at -2. -2 times 3 is -6. And again, very hard for me to draw. But that's our vertical stretch. So the distance in between steps now is more. So it's at 0, 3, 6, -3, and -6. I'll try to orient the board one more time.
What was the last one? What was the
negative? -6. Because originally we had a stair step at -2. There, moved it up a little bit. So the 3, which is on the outside, causes a vertical change. The 1/2 is on the inside of the function. How does that change our function? Remember, we have to take the reciprocal to figure that answer out. Well, this reciprocal of 1/2 is 2. And what happens is this is a horizontal change. And again, when we take the reciprocal of 1/2, you get the 2. we're also going to have a horizontal stretch by a factor of 2. So where our stair steps are now isn't going to change. But the length of our stair step now is going to change. We're still going to have a stair step starting at the origin, but instead of it being a distance of 1 unit, and that's supposed to be an open circle there, it's going to be 2. Because horizontally, we're going to make the step longer now. But again, where the stair step isn't going to change. We're still going to have a stair step here at 3, but the length of our stair step is going to be longer. Instead of being a distance of 1, it's going to be a distance of 2. And we're still going to have a stair step at 6, but the length of our stair step is going to be longer. And usually with this type of function, again, once you see the pattern, you could continue on forever. There's always a space of 3 in between. So our -3 stair step is still there. And then we also have a stair step at -6. They're just a little bit longer. Open circles to the right on our stair steps. That's what we need to practice here for the next few days. But to finish here, let's look at our graphs. Let's look at a couple pictures of graphs and figure out and figure out the equations of the graphs. So we still need to be able to identify the parent function, which is in this kind of purplish mauve color. That's going to be the parent function. And then our aqua colored graph is going to be the transform function. So it says the graph of a parent function and transformation of the parent function are given. Write the equation of the transform function. So what I found helpful, and I don't have space here to do it, is out to the side I wrote down what the transformations were. But we also need to identify what is the parent function in problem number 5. It's going to be the x cubed, so we need to know that. So I just write somewhere around my graph that's going to be x cubed. And then what we need to look at is we need to figure out what the transformations are. So we're going to have to find out what's happening to this graph. Well, if you think back to y equals x cubed, we actually have a point at 0, 0. And it's really the center of the graph. So I wonder if we can find the center of our transform graph. And if you're looking fairly closely here, I think you would see, if I can get it in there, that it's here. And what that's going to tell us, at least, is going to tell us how the graph moved. We went 1, 2, 3, 4 spaces left, and we went 1, 2, 3, 4, 5 spaces down. So there's 2 of the transformations. 4 left, 5 down. And in fact, that's the only thing that I can identify on this graph. Grace? So now what we know is we can write our equation. So you can write y equals or f of x equals. It doesn't make any difference here. It's an x cubed function, but 4 left means that we're going to have x plus 4 cubed. And then we're still going down. There's the minus 5. So now, on problem number 6, again, what we need to identify is what's the parent function. And then after we know what the parent function is, and I really probably should have written p of x. Sometimes that's what they do, p of x for parent function. And what we've got here is our mob graph. That's our parent function. And it's a little bit hard to read because it kind of looks like it's a dotted graph here. It's just that they left room for the axes to show, or the grid lines to show here. So it's not really a dotted or dashed line there. And one thing that I'd just like to show you on this one is that, well, our parent function is 1 over x. And if you think back to our parent function notes, we talked a little bit about how there's an asymptote in this problem. And in fact, what happens is that our graph, our parent graph, never touches the y-axis, nor does it touch the x-axis. And so what I like to think in terms of on this graph is, well, where did those asymptotes move to on our graph? Well, if we're really looking here, it looks like in the aqua graph that we have an asymptote right there. And it also looks like we have an asymptote right here. And what those two can tell us is they can tell us how the graph moved, like our 4 left and 5 down over here. It's the same kind of idea. And it looks like we moved 2 left on this graph. And then we moved 1 up. But we do have one more change in this graph, one more transformation, a better word. And it depends on how you look at things. But I usually, if I have an option, will go with the outside of the function option. So what I said is that this graph reflects over the x. So this went over here and moved. This went up here and moved. So I said that we reflect over the x-axis. And once we identify that fact, then we can write our function. The thing is, can you argue a case for reflecting over the y? Yes. But I prefer, personally, for the outside of the function. And we can talk in a couple minutes if you want to look at it from that perspective. But the reflection over the x-axis means that we're going to have a negative directly out in front of our function. Well, our parent function is 1 over x. But what we know is we're moving this graph 2 spaces to the left. And that means it's going to be the plus 2. And then finally, for our 1 up, we're going to add 1 to our function. So one last picture here, and pictures sometimes are a little bit harder, especially when you don't have the color coding on your paper. But here's our last function to look at. And again, there's 2 ways to look at this function. But as we do look at this, I hope that you notice that the parent function is the absolute value of x. So then there's actually only 2 things happening to this graph, 2 transformations happening to this graph. Can you name one of them? Right 2. That's the one that jumps out at you, or at least I hope. Our origin moved over here. And then the other one, again, there's 2 ways to look at this. But what I said is that this one is a vertical stretch. And I know on the video you can't see my hand gestures, but what happens here is if we take this graph and we stretch it vertically, what happens to our horizontal distance? It also compresses horizontally. So if you go this way, not only does it impact this way, but it also impacts the horizontally. But I think that it's easier to see in terms of the vertical stretch. If you notice on this graph, the mauve graph, the purplish mauve graph, we went one space to the right, one up. One space to the right, one up. One space to the right, one up. Every single time. Absolute value of 1 is 1. Absolute value of 2 is 2. Absolute value of 3 is 3. If we look on this graph, what happens is we actually ended up going one space to the right still to find a whole number point, and then we went up 4 spaces. Tracy? You could look at it either way. I chose the vertical because the vertical is an outside concept. When it's on the inside, sometimes it messes things up a little bit in people's minds because you have to go the opposite way of what you think it's going to do. So on this one here, I said it's a vertical stretch. And like I said, in the original graph, we go right 1 and up 1. In the new graph, we went right 1 and we went up 4. So we vertically stretched this by 4. And once we can determine that, we can write down the equation, and I can show some of the rest of you who want to see the horizontal the answer here in a little bit. But in terms of our function then, what we've got is we've got f of x equals, well, that's the absolute value of x. To move right 2 this time, we're going to have to subtract 2. And our vertical stretch by a factor of 4 is going to come outside of our absolute value.